Now let's say steady state analysis of resistance, inductance, capacitance with sinusoidal excitation. The steady state analysis refers to analysis of circuit at a state or condition after the transient or natural response died out. Usually steady state is achieved after 5 times constants of the switching action, and analysis at this state is carried out using phasors. The term steady state response is used synonymously with forced response, and the circuits we are about to analyze are commonly said to be sinusoidal state. Yeah, please look into this complete chart. We have taken an element, 3 different elements: resistors, inductors, capacitors, and for each of the element we will study what is the unit, voltage, current, impedance, power, energy, and how the characteristics are. So let's take the first element as a resistor. The unit for this is ohm. Voltage is nothing but, according to Ohm's law, V is equal to IR. So the current will be equal to V by R. The resistance will be equal to V by R. And power is nothing but product of voltage and current. So we can write V into I, and V is nothing but IR. So this comes like I square by R, or in terms of V, power can be written as V square by R. What is energy? So it is nothing but integration of P into dt. So it is nothing but with respect to product of power and time. So this can be written as V into I. Now the characteristic is, if R is equal to 0, then what will be I? I will be equal to infinity, and V is equal to 0, short circuit condition. And if R be substituted as an infinity, then I is equal to 0 and V is equal to infinity. So this is called as an open circuit condition. So this was all about the element called resistor. Next, if we consider an inductor, the unit for the inductor is nothing but Henry. And here voltage is proportional to d phi by dt. This is magnetic flux. And according to Faraday's law, this magnetic flux is nothing but, it is directly proportional to the current flowing through it. So phi is proportional to I. So the same thing we can write it as proportional to di by dt. So if you remove the proportionality sign, so we can write the voltage with respect to time is equal to L di by dt. L is nothing but self-inductance, and the unit for inductance is Henry. How you'll calculate the current? So voltage is equal to what? The integration of Vt with respect to dt is equal to integration of L di by dt. So if you integrate this, we can get the value. Integration of di is nothing but I. So if just calculate this mathematically, so I is equal to 1 by L integration of Vt dt. Similarly, what is the value of impedance? In fact, what is impedance? It is nothing but joint effect of resistance and reactance. So if you know the value of I now, you have known the value of I, you can, I is nothing but I max into sin omega t, and V is equal to L di by dt, or in terms of I, if you substitute over here, so this is omega L I max into cos omega t. So impedance is nothing but V by I. So if you substitute both the value of V and I from here, you will get it as impedance is omega L sin omega t plus 90 divided by I max into sin omega t. So from here we can say that the impedance is equal to j omega L. Similarly, power is nothing but voltage into current. So if you substitute all the values, so this comes like Li into di by dt. And energy is integration of P into dt. So this comes like half Li square. The last is characteristics if you want to understand. So this is di by dt. If it is 0, then V is equal to 0. This can be called as a short circuit condition for DC. and di by dt is positive, so the power will be positive. So here L absorbs power and charging, whereas if you see the di by dt is equal to infinity, the power will also be infinity. Here we can say that the L supplies power. It means it is discharging. And if at all di by dt is equal to 0 and power is equal to 0, then L is idle. It means that di by dt is equal to infinity. So L does not allow sudden change in current. So energy across L is finite even if V is equal to 0. The last element we will consider about the capacitor. The unit for capacitor is farad, and integrating current of the capacitor. So if you integrate I dt, so this is nothing but C dV by Q, because C dV by dt, because Q is equal to CV, charge is equal to CV. So and Q is nothing but the rate of flow of charges. So after all integrating, we can get it as V is equal to 1 by C integration of I dt. As C is equal to Q by V, Q can be written as CV. So dQ by dt is nothing but C dV by dt, and dQ by dt is nothing but the rate of flow of charges is nothing but current. So current is equal to C dV by dt. So we have found the value of voltage and current, and the impedance is nothing but V by I. So if you substitute V as in V max sine omega t, and I as an omega c V max cos omega t. So if you substitute the value of V and I over here, so XC you'll get it as 1 by j omega c. So this is called as an omega L is inductive reactance, and 1 by omega c is called as an inductive capacitive reactance. So the power is nothing but V into I. So this comes like CV dV by dt, and energy is integration of P dt. So this comes like half CV square. Now for here, for the characteristics how it behaves is, if dV by dt is 0, that is the current is 0, it can be called an open circuit for DC circuit. So C absorbs power and charging. If dV by dt is equal to minus infinity, then C supplies power or discharging, and if dV by dt is equal to 0, then we can say that C does not allow sudden change in voltage. And energy across C is finite even if I is equal to 0, because we have energy is equal to half CV square. Now we will feed the AC current to an individual components called resistance, inductance, and capacitor. So let's understand the behavior of pure resistor in an AC circuit. This is an AC circuit given to a pure resistor. This is the flow of the direction of the current in the circuit, and the potential difference across R we have taken as a VR, and this is the voltage, AC voltage, which is nothing but V is equal to V max into sine omega t. So what is current? Current is nothing but V by R. So V max sine omega t by R. So V max by R, because V max is the total current, maximum current in the circuit, and the total value of resistance is R. So V max by R is nothing but I max. So we can write as an I is equal to I max sine omega t. So waveforms and phasor representation. So this you can see that this is a current because it's a sinusoidal wave. It will start from its mean or zero value. So this red color represents the current, whereas this blue color represents the voltage value. So we can understand from these two graphs this is a maximum current and this will be the maximum voltage. This is in radians, pi by 2, pi, 3 pi by 2 and 2 pi, and this will be minus I max and this will be minus V max. So from here we can understand that the voltage and current are in phase with each other because it is very in phase with each other. So what is impedance? Impedance is nothing but V by I, V max by I max. So this is nothing but it will come as a capital R. And the phase difference and power factor, phase difference is equal to pi and angle is equal to 0 because there is no phase difference. And the power factor is cos phi. This is represented as cos phi. Where the phi is 0, so cos 0 is 1. So power factor for this particular resistor is 1. And what is power? Power is nothing but product of voltage and current, and V is equal to V max sin omega t and I is equal to I max sin omega t. So this comes like Vm Im sin square omega t. Sin square omega t we can write as 1 minus cos 2 omega t. So this 1 by 2. So we have written Vm V max by I max by 2 into 1 minus cos 2 omega t. So this finally we can write as an V max I max by 2 minus V max I max by 2 into cos 2 omega t. So the power we can write in this form. The power consists of a constant part V max I max by 2 and a fluctuating part V max I max by 2 into cos 2 omega t. The frequency of fluctuating part is twice the applied voltage frequency and its average value over one complete cycle is 0. So what is average power now? Average power is equal to V max I max by 2, or we can write it as V max by under root 2 into I max by under root 2. So this is nothing but power average is equal to VRMS into IRMS. So graphical representation of current, voltage as well as power. So this is current, okay, and this is a voltage, and this is a power. And this is a maximum power. This we represent this as an average power. Similarly, now the pure AC current is applied to a single inductor, which is it's into the pure form. So considering an AC network connected to a pure inductor L in series, we can see over here. So the potential difference, the voltage across this particular inductor is PL. This is a sinusoidal voltage. V should be equal to V max into sin omega t, and I is the direction of the current. Here is shown. I is the current in the circuit. So how the I is found out? I is nothing but according to the Faraday's laws of magnetic induction, phi is proportional to I, and di by dt is nothing but Ldi by dt. We can form in the we can write it in the form of current because phi is proportional to I. So with that equation, I is equal to 1 by L integration of V dt. Or we can substitute the value of V dt is nothing but V is equal to V max sin omega t. So if you substitute and integrate, this finally gets as current in the circuit is equal to I max into sin omega t minus pi by 2. Minus pi by 2. So if you see waveforms and phasor representation, let's observe this. So this is a current, this is a current, and this is a voltage. Okay, so with respect to voltage and current, we can see that as per the equation I is equal to I max sin omega t minus pi by 2, it means the current is lagging the voltage by 90 degree. So this is how we have represented it. This is as usual the voltage from its mean position, V is equal to V max sin omega t, and because it is lagging by 90 degree, this is a 90 degree, so lagging, so from minus direction with a 90 degree angle, this we have represented as a current value. So this is a voltage and this is a current. This is how it is going on. And the self-induced EMF, we can say that this is a self-induced EMF. So according to phasor diagram representation, this is a voltage. So the current lagging, here we can see that the current is lagging the voltage by 90 degree. So this can be a phasor representation. Now what is impedance in this? Impedance Z is equal to V by I. So we can substitute V as in V max and all, and this is I max and whatever the value we have. So if you substitute, so finally we can get it as it is J omega L. So the impedance for the inductance is omega L. This quantity omega is called inductive reactance because this is the resistance produced due to the inductance can be called as an inductive reactance, which is denoted by XL, and the unit for this is nothing but ohms. Significance of operator J is used in a rectangular form. It is used to indicate anti-clockwise direction of phasor through 90 degrees. So mathematically, J is equal to J square is equal to -1. So the phase difference is 5. So here we can see that it's 5 by 2. So the degrees angle is 90 degree, and form factor is nothing but cos phi is cos 90. So cos 90 will be equal to 0. And what is power? Power is equal to V into I. So we have just substituted the value of V as V max into sin omega t, and I is equal to I max into sin omega t minus pi by 2. So if you solve this, you'll get it as minus V max I max by 2 into sin 2 omega t. And average power will be equal to integration of instantaneous power. So this comes like 0. So what is the power consumed? You can see from here. This is V value, and this is an I representation, and I representation, and this will be the power one. This is the power. Now the last component, we are connecting an AC current to a pure capacitor. So the voltage across the two plates of the capacitor is VC. I is the current in the circuit, and V is equal to V max sin omega t, as usual we have taken. So the current is nothing but C dV by dt. So C into d by dt of V is nothing but V max into sin omega t. So if you calculate this, this is nothing but omega C. If you derivate this, sine side is nothing but sin omega t, it becomes like omega cos omega t. So this comes like omega C V max into cos omega t. So we can write the same omega C V max cos omega t or cos omega t in terms of sine. So I is equal to I max sin omega t plus pi by 2. So this comes like, this is nothing but it means the current here from this formula with respect to this V is equal to and I is equal to, if you compare these two, it means the current is leading the voltage by 90 degree. So this shows the phasor representation. This is the current is leading this voltage by 90 degree. So this is counterclockwise direction, and here we have represented the blue line as a voltage. You can see here, and this as an current representation. So current is leading the voltage by 90 degree. You can see here from the blue curve. So this will be I max, the maximum or amplitude value of the current, and this is V max. We can say it is an amplitude of voltage. Impedance as usual is V by I. If you substitute the value of V and I over here, so you'll get it as Z is equal to minus J XC. So 1 by omega C, here you can see that minus J by omega C or minus J XC. So what is this XC? XC is nothing but 1 by omega C, which is called as an capacitor reactance, and is denoted by XC, which measures in ohms. We have already told the significance in an operator. So the phase difference is phi. It is nothing but 90 degree, and power factor is cos phi is nothing but cos 90 is equal to 0. So what is instantaneous power? So it is V into I. We just substituted V max sin omega t, and I is equal to I max sin omega t plus pi by 2. So if you do this mathematics, it comes like Vm Im by 2 into sine 2 omega t. So average power is equal to integration of instantaneous power, which comes as 0. So here you can see that this is a voltage, this is a voltage, the green one is current, and this is a current because it is leading the voltage by 90 degree. So the dotted one represents the current and the green one represents the power. Now the summary of all the three components when we have applied an alternate current to resistor, capacitor and inductor. So if you summarize this, you kind of a impedance table. So the symbol for resistance is R and the value of resistance or impedance is Z. Phase of the current, we can say that it is in phase with the voltage. So phase constant is 0 and amplitude relation will be VR is equal to IR into R. In case of capacitor, the symbol is C. The impedance is 1 by omega C. And here the phase difference is, it is leading the voltage by 90 degree. Phase constant is minus 90 degree or minus pi by 2. And the VC value is equal to, amplitude relation is VC is equal to IC into XC. And the last for the inductor, the symbol is L. The reactance, we can say it in the form of impedance is XL is equal to omega D into L, and it is lagging by 90 degree. So this is phase constant is plus 90 degree or pi by 2, and amplitude relation is VL by VL is equal to XL into XC. Now, previous slides, we have seen the alternating current when it is passed through a pure resistor, inductor, capacitor individually. Now we will see and connect the resistor and inductor in series and pass the alternating current and understand the behavior of the circuit. So let us consider a circuit containing an alternating current of voltage V is equal to V max sin omega t, connected through a resistance of a value of R and an inductor, a self-inductor of value of L in series as we can see in this particular circuit. So let V is equal to V max sin omega t, and capital V and capital I are RMS values of source voltage and current, and we can say that VR is equal to RI and the voltage across resistance is equal to R into I, and where VR and I are in phase, because in the case of resistance we have studied the current is in phase with the voltage, and for the inductance across, this is a VL across the inductor is equal to I into XL, and here I lags VL by 90 degree. So here with respect to the phasor diagram you can see that this V is equal to VR minus VL. So from the vector diagram very clearly we can understand. So V is coming like this is VR, this on the X direction we have taken as an resistor, and for the Y direction we have taken as an inductance. So this comes like V is equal to VR minus VL, and this is the phase angle. Here you can see that this blue represents the voltage, and this is current because it is lagging. It is lagging by how much? It is lagging by 90 degree, and this pink graph curve represents the power. So on this axis we can see that power, voltage and current with respect to instantaneous time. So what is impedance here? The impedance is nothing but, as we have seen from the phasor diagram, this is plus. V is equal to, according to the vector addition, so V is equal to VR plus VL. So if you substitute this, V is equal to VR plus VL, and substitute the value of voltage. VR is IR and VL is equal to I j omega L. So we can get the value of impedance. So impedance is nothing but V by I. So if you substitute this, I will get cancelled. So Z is coming as R plus J omega L. So, or the mod, if you take Z is equal to mod of Z is equal to under root of R square plus XL square. And XL is nothing but omega L. So if you substitute all this value, the impedance is coming as under root of R square plus omega L square, and phi is equal to tan inverse of XL by R. Impedance triangle, if you see, the right angle triangle formed with the vectors representing the resistance drop, the reactant drops, and the impedance drops of a circuit carrying an alternating current is called impedance triangle. So this, we can say this is a impedance drops, this is a resistance drops, and this is a reactance drop. So from here you can say that Z is equal to, according to Pythagoras theorem, it's a right angle triangle. So Z is equal to under root of R square plus XL square. And from here, sin phi is XL by R, opposite by hypotenuse, and cos phi is adjacent by hypotenuse, and tan phi is opposite by adjacent. And here if you calculate the current is nothing but which is equal to IR or equal to IL. So it is coming like I is equal to Im sin omega t minus phi, where Im is equal to Vm by Z and phi is equal to tan inverse of XL by R. So this is actually what we need to find out for any of the combination, whether if you take RC, RL or LRC. So finally we need to find out the value of I. So we have assumed I as an I is equal to Im sin omega t. So here we need to find out the maximum current as well as the phase angle. So then we can say that that's a complete equation. And power we have substituted is product of voltage and I. Substituting the value of voltage and current, we'll get it as Vmax by Vmax Imax by 2 cos phi minus Vmax Imax by 2 cos 2 omega t minus phi. So if you calculate the average power, it is integration of instantaneous power. So finally it comes as Vrms into Irms into power factor, which is nothing but cos phi. So from here we have the average active and apparent power. So active power is dependent on in phase component of the current. The average power is the full power that is used to do work on the load. Active power is also called as an average or real or true power and is measured in watts. So active power is nothing but P is equal to VI cos phi. Reactive power is pure inductor and capacitor consume no power because all the power received from the source in a half cycle is returned to source in the next half cycle. This circulating power is called reactive power. It is the product of voltage and reactive power of the current, that is I sin phi, and is measured in kVr. It means voltage ampere reactive. So Q is equal to VI sin phi. The last is apparent power. The product of voltage and current is known as apparent power and is measured in kVA, kilovolt amps. So apparent power is equal to S is equal to VI, which is nothing but under root of P square plus Q square. And if you see the power triangle is a representation of a right angle triangle showing the relation between active power, reactive power, and apparent power. When each component of the current, that is active power, active component or the reactive component is multiplied by the voltage, a power triangle is obtained as shown in the figure. We can see this is a real power, reactive power, and apparent power. With each of the values specified. And power factor is nothing but cos phi. and you can see the power factor from the voltage triangle VR by V, from impedance triangle R by Z, and from power triangle it is P by S. So in case of series LR circuit, the power factor is lagging in nature. This is complete the synopsis. A circuit diagram with a phasor diagram, impedance triangle. This is the current is lagging the voltage by phi angle. Okay, and this is a resolution of phi, and this is all about the power curves.